The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you for the opportunity to speak with you this afternoon. And I will say, Doug, thank you very much for being a setup guy. You're a great setup guy because it's very fortuitous. A lot of the things that he said, we're going to cover in a little bit more detail and get down into the nuts and bolts with this presentation. Before I begin, as Kimberly said in the opening, some of the ideas and opinions expressed in this are not necessarily indicative of opinions held by ACI. As with my presentation here, I may make reference to some software or particular programs. You should not consider those to be an endorsement of ACI or LJB either. So for our agenda for this particular portion of the presentation, we're going to look at some of the design considerations that surround that cylinder wall tilt-up panel. Look at very briefly an example calculations that we might do through the ACI 318 procedure. Compare that to some finite element models for a handful of panels, and then get really into some non-standard panels that we're often encountering beyond a warehouse type structure that Doug just spoke about. So when we're looking at a cylinder wall, we have in a tilt-up panel a lot of things going on. We've got the wind pressures, the seismic forces, we've got the load from the roof and the floors, and they all act in a certain way. And for the vast majority of tilt-up panels, you do have an axial force. It's often eccentric. As Doug mentioned, he often considers that force to be at the inside face of that wall panel. And then you've got the primary out-of-plane force. But since these walls are cylinder, you do have that secondary moment. We'll talk a little bit about that in a minute. In general, as engineers, we're considering a simply supported model of our panel. That is, it's pinned at the base, it's pinned at the roof, or whatever support may be at the top of the panel. So it really acts like a simply supported beam. So in looking at the combination of those forces, the primary loads are the eccentric axial force and then the out-of-plane pressure suction on the panel. Those act together as a primary moment. The secondary moment that we referenced is from that P delta effect. So as those loads apply, that panel bows, and then that creates a secondary moment from where that axial force and the weight of the panel makes it bow even more. And that combined moment is what we need to consider as panel engineers in our design. Previously, the idea would be to iteratively solve for what the panel reinforcement would need to be. You get your primary moments, find out what the deflection of the panel is, get your P delta effect, plug that back in as your moment, and continue to iterate until you reach some level of convergence that you are comfortable with. The procedure in 318, though, involves more of a moment magnification method, where you define the stiffness based upon the crack moment of inertia of that panel, and you rewrite your displacement, your delta term, in terms of that moment and stiffness relationship. It's important to note that with the moment magnification method, it's a singular solution. You don't have an iterative procedure. As I said, the crack moment of inertia uses an effective area of steel. And I just want to pause on this because you have what you're specifying as a design, or what your vertical reinforcement is. The second component of that is taking advantage of the compressive force within the panel that you already have from that axial load. You see in that second term there, we're acknowledging the fact that that panel in its vertical state does have some pre-compression to it. And in order for the tension in that primary reinforcement to be engaged, it has to go from that compression through zero and into the tension. The H over 2D is an acknowledgement of the fact that that compressive force is dependent upon the location of the steel. The more the steel is centered within that panel, you can rely completely on the compressive force. The more it gets out to the outside faces, you can see that can be almost up to half contribution. So your efficient selection of reinforcement is really that point there where your FINITE intersects your MU diagram. And I'm going to pause here and just say that this is a theoretical diagram. Obviously, there's no point, you cannot reinforce a panel with sufficient area of steel that you're ever going to get no moment on the panel. That's not the case. But this is a theoretical exercise to demonstrate to you that there is a point where you need to have at least sufficient amount of steel that you overcome that stiffness comparison to the axial load being applied. If you don't, then your analysis is actually going to diverge in terms of your overall maximum moment that's applied to the panel. Obviously, the most efficient section is right there where the two graphs are intersecting. There are other limits within ACI that would bring you further to the right of that graph. So let's look at some of the calculations that we have when we're talking about slender wall. Let's just take a plain panel, for instance. It's 6 1/4 inches thick, has 3 joists bearing on it, and then it's subjected to an out-of-plane load from wind. We'll apply a total dead load of 7.2 kips, a live load of 7.5 kips. We'll use Doug's recommendation for an eccentricity of about the inside face of the wall. And then we have the loads acting 1'6" down from the top of the panel. So our overall unbraced length is 29.5 feet on this panel. We'll look typically as an engineer, we'll look at these 3 main load bases to compare our reinforcement. I'm only going to go through the first one that's highlighted, and you'll see what the results are. But we're going to assume to start out with 15 number 4 bars in each face. So we've got 2 layers of steel as illustrated, so 3 square inches of reinforcement. We go about calculating our applied factored loads to the panel. Now, those are separated out into 2 different categories here. We have the applied load from the joists on the roof, and then to that we've added the contribution of the mid-height section of concrete of the panel itself, because that does contribute to your P delta effect. We've got our factored out-of-plane wind load, and Doug in his presentation referenced the 6% of your compressive strength of concrete as a limit on your axial load. So we do want to have a check against that. And again, your panel is a portion of that axial load as you're making that check. For this particular case, we're going to continue on with the ACI 318 method. So let's look at the effective area of steel. And we made reference before about using that contribution of the loads from the panel and from the roof load. You can see that gives you in excess of 2 extra bars theoretically, 3.45 as opposed to the applied 3 that we have in our supplied 3 square inches of reinforcement. So you've got almost 2 full bars that are contributing just from that panel stress. Continuing on, we'll make sure that we've got a tension-controlled structure. We've got our calculations for our cracked moment of inertia that takes into account that effective area of steel. And we calculate that our nominal moment capacity is, in this case, 75.1 feet. Now we'll take that and compare it to what our maximum moment is, or ultimate moment. We calculate our stiffness, and we're calling that our KD B value. And using that, and with our applied moment, the out-of-plane, the WL squared over 8 is where all of the engineers in the room are familiar with for a simply supported beam model with uniform load. And then our applied axial force acting eccentrically. Using our moment magnification method, we get to an applied, or a maximum moment, of 38, which is much less than what we looked at before for our nominal moment capacity. Again, you're going to go through several different load cases, and if you were to go through the second one that we presented here, you find that our solution using 15 number 4 bars actually very closely relates the maximum moment and the nominal moment capacity. Now let's look at something where if we have an opening in a panel. The plain panel is fairly straightforward, but how do we treat this particular panel? And how do we design around this opening? It's very common practice to use the tributary area. So in this particular case, that left leg, a 4-foot leg, is going to have a tributary area associated with that yellow block there. Likewise, the 6-foot leg on the right is going to have the tributary area associated with that blue block. In doing that, we get a solution through 318 that has 10 number 4 bars on the left leg and 11 number 4 bars in the right leg. Let's look, though, about some finite element comparisons, because we've talked about a simplified procedure that's provided in ACI 318, but how does that really compare to what's going on with the panel? If you recall, we just looked at 2 panels, a plain one and one with an opening in it. In our first solution with that plain panel, we had 15 number 4 bars in each face. The finite element model gives us a little bit better view of what's going on with that particular panel. You can see here that it's given us a slightly better solution. We've got actually 15 number 4 bars if we average it across that full width. The reason why it's doing that is because it's not taking all the limitations or the things that we neglected, I should say, in the 318 procedure. You still got the contribution of the negative moment region for the parapet at the top and some other. So you've got the contribution from the negative moment that reduces the positive moment at the parapet and some of the other limitations on the strength and stiffness of the concrete. You'll also notice that the finite element model tells us a lot about that free edge of the panel and how actually that compressive force is more into the internal portion of the panel. Similarly, let's look at the panel that had the opening in it. Again, our solution from 318 was 10 number 4s each face in the left leg, 11 number 4s each face in the right leg. Finite element model, again, gives us some savings from that design. But you'll also notice how it accurately represents what the stresses are in the corners of that opening. Just for comparison's sake, what if we were to take this panel and analyze it with this 2-foot strip loads on either side? See, that's something that we could do now because of the tools that are available to us with the finite element model package. If we use the 2-foot strip on either side of the panel leg, we could come up with a solution using number 4 in each face. That would be rather tightly packed reinforcement, and I encourage you to consider other options in that case. But this gives you an illustration of some of the tools that are available to us that we hone in on different solutions. With the time we have left here, I want to look at modeling some of the non-standard panels. Certainly a plain panel with a singular opening that's 1 story in height is something that we all encounter. But there are a few other panels that Doug just gave us an illustration of. Those would be ones with canopy loads, ones that are set on isolated foundations, be they piers or spread footing underneath the panel joint, screen walls, or retaining walls, and then finally multi-story panels. So Doug spent some time talking about the contribution of that canopy into your moments in the panel, and specifically the snowdrift that would go on that, and how much, I'm looking at John here in Colorado, he knows what that snowdrift is like. You can see here an idealized, again, application of that load and how that translates into the panel moments, and that doesn't really fit in to what we've seen in our previous graph with a nice curved bow, again, simply supported model. So how do we treat this? Well, we can conservatively just add that piece of that moment created by the canopy load to our applied moments, and then again use the moment magnification method to run through that analysis. It's important to note, though, that that P delta effect that we talked about, contribution of the road loads, the weight of the panel, also needs to include the weight of this canopy in your analysis. So The plane panel that we looked at with just roof loads and out-of-plane forces on it, we had 15 under force in each face. In this particular case, as Deb referenced, sometimes it doesn't add a lot. And the same panel with the canopy load, we only had one more bar in each face. We also commonly find this situation with concentrated vertical loads. A lot of times we're used to dealing with them and from a building engineer perspective where we have a high girder load or very high loads from the roof or from the floor beam. But this can happen when you have, again, panels on drilled piers or caissons or a pier cap or something where it's not a uniform load across the base of the panel. So what you see here is an idealized model of how you should analyze that. You cannot count on the full effective width of the panel. You have to have a design strip that's illustrated here. So our concentrated load, let's take an example here, expand our original to 20-foot wide, just for illustrative purposes, so you can see at our center line of our unbraced link, we actually have less of the panel to count on. And you can see in the end product how we concentrated more than reinforcement into those legs and just use nominal reinforcement in the middle. Screen walls can easily be adapted using the ACI 318 procedure. Yes, they are cantilevered, and yes, we spent the past 20 minutes talking about a simply supported idealized model. But we can get to a screen wall solution by realizing that as long as twice the cantilevered length would equal a simply supported, the length of the simply supported span, we have basically the same calculations. I say basically the same calculations because that's true from the strength perspective. But from a deflection perspective, you have to use judgment about the serviceability deflection that you want to consider for a screen wall as opposed to a building element. And the final thing I would like to talk about is multi-story construction. Doug actually showed us a picture of the final building. This is a construction photo of a 6-story building in the Woodlands, Texas. Now, obviously with the 6-story building, we've got several areas of support along the floors and at the roof. But there are some conditions that you should be aware of as an engineer, be it either the engineer of record or the panel specialty engineer. You could have the simply supported scenario in your temporary condition where you have support at the foundation or your brace attachment, or some other construction period condition where you have the foundation support, maybe a floor in place, and the braces have been removed. The final condition, obviously, and especially in a situation like this, you have very high axial loads coming down into those panel legs. Sometimes, and you've got to resolve, in this particular case, that load cap, getting it from the upper floors down through, transfer through the transfer beams down into panel legs that go all the way to the foundation. Those panel legs at the bottom also have positive, out of plane and in plane moments. The axial load due to a lot of the panel self-weight, as we said, the gravity loads of the floor and roof, and also the load from overturning. Doug commented on this in his big box presentation about joining 2 panels or 3 panels together, and as that overturning comes in a multi-story design, especially one that has the panel with so much opening area in it, you do have an added axial load in those legs because of that overturning effect. Obviously, you've got the out-of-plane loads and the moments associated with that from a wind or even in a high seismic area, that force acting perpendicular to the plane of the panel. But that overturning also creates in-plane moments between your beam sections and the panel that have to be considered. So often what that leads us to in a 6-story, multi-story type design is not a simply supported beam model, but more a column with biaxial moments. I know a lot of engineers use that type, or you can get into higher order type analysis, like a finite element model or even a frame model to complete this type of design. Are there any questions about what we have? Yes, sir.
The software we're using for the finance,
SQ wall. Yes, sir.
I was just wondering, you talked about the basically P little delta effect. Are you accounting for big delta from like maybe the diaphragm drifting and the panel actually leaning?
So the question is, are we accounting for the effect of the diaphragm leaning and creating a difference between where the cloud load is over the center of gravity of the panel? I say that I know that there's a lot of engineers, especially people in this room, that do that. That's not something that we've covered either with the ACI 551 document or it's been in the slender wall procedures, but I know that that's definitely something that a lot of engineers do consider in their designs. Well, I'd be happy to stay after if someone does have a question that comes up. If it perhaps is beyond the convention, I encourage you to contact me by any of these ways. Thank you very much for your time.